invite Patrícia. Okay. She has a degree in mining. She has a master's degree from the Federal University of Minas Gerais, and she's currently a professor at the Federal Institute of the state of Pernambuco. She has experience in mining engineering, and she works mostly on the sedimentation speed, flocculation, Fisher tests, coagulants. Okay, thank you, ma'am. The floor is yours. Good morning, ladies and gentlemen. This paper was done jointly with Mr. Jorge Soares Valadão. We worked with tailings from phosphatic sludge, and so it's an experimental planning applied to the phosphatic sludge sedimentation process. So the sludge is generated when we are processing ores. And this sludge contains a lot of fine particles, and when it's in water, the fines remain in the water. So normally speaking, we work with coagulants and flocculants, and they are used to promote the sedimentation because these particles are stable in the water, and I need these fine particles to become sedimented. So, and how do we do that? By using reagents. And I worked with experimental planning based on statistical principles. Okay? So what do I have to do in order for the particle to become sedimented or go through sedimentation? I use the coagulation process. How does it happen? It happens with attractive forces that overcome the repulsive forces, and I try to minimize this repulsive energy barrier. How do I do that? I change the superficial electrical load by using determinant ions, okay, using the potential IDP, and I control the pH. I neutralize the electrical charges, promoting the adsorption of specific ions, okay, so that I can lower the zeta potential. And I also do this by compressing the double electrical layer, and I add electrolytes. And we have the mechanisms for aggregating the particles via flocculation. Okay, so I work in a binding agent, usually a high molecular weight polymer, and it unites the particles via bridges. I work with the characteristics with the sedimentation of the particles. Okay, I prepare a pulp, and this pulp starts sedimenting throughout time. This is the part of my work, okay? The most important part of my work. I also use experimental planning. By using factorial planning, it allows me to vary experimental conditions at the same time, but in a controlled and planned way. This method involves using higher, superior, and inferior levels. And so these experimental level parameters, they can be combined among themselves with a synergetic effect of the variable so that we can assess everything. So what were the materials and methodologies? We used sludge that came from phosphate ore from the company called Vale do Rio Doce in Minas Gerais. We carried out the mineral characterization using X-ray. We also use sedimentation tests using commercial flocculants, cationic types, anionic types, non-ionic types, and aluminum sulfate coagulants. And the sedimentation tests were carried out in pulps containing 10% of solids, okay? And we also use several different doses, and after that we use a pre-coagulated and pre-flocculated pulp. We also did sedimentation tests with pre-flocculated and pre-coagulated pulps in different pH levels, determining the sedimentation speed for each test. For the Yates algorithm, so what happened? We worked with a pulp. I worked with a cationic flocculant, okay, anionic flocculant, and a coagulant. So I carried out the coagulation and the flocculation, and I worked with the Yates algorithm. For the cationic flocculant, I worked with a pH between 12 and 6. For the coagulant, aluminum sulfate, I use 99.44 per ton. That's for the superior level. And for the inferior level or the upper level, 99.44. The lower level, 27.62. For the cationic flocculant, 22.10 for the upper and 5.53 grams per ton. For the anionic flocculant, I varied the pH between 12 and 6.5. For the aluminum sulfate, okay, the same dose of the cationic flocculant was the same, and for the anionic flocculant, the same dose. For the non-ionic flocculant, I use a pH between 12 and 6.5, the same amount of coagulant and the same amount of flocculant. For the cationic, anionic, and non-ionic flocculants, I defined upper levels, lower levels, the same, and the coagulant dose, okay, the same. What were the results that we obtained? In my sample, we saw percentage of calcite, magnesium calcite of 80.57%, 11.10% of dolomite, 6.72% of apatite fluoride, and 1.6% of magnesium biotite. The sample was an ultra-fine sample, and the D50 of the particles was 5.1 micrometers, classified by the IUPAC of micropores. The mathematic modeling, I varied the pH and also the amounts of coagulant and flocculant, and the analysis of the results, interactions have shown to us, and we can reach the following conclusions. In the highest influence variable, the dose of flocculant for the cationic flocculant. Why? Because when you go from a lower upper to an upper level, a lower level to an upper level, when I define, you can see this on the table, the annotation A as TH, C as the amount of flocculant. And in the table, when there is a difference, you can notice that the highest influence here came from and the second most influential variant is the dose of flocculant. But when it goes from the lower level to the upper level, the impact becomes negative. And via this mathematic modeling, I was able to arrive at an equation proving what I have just said. So the values that were forecasted and the experimental values. So this is a chart that shows to us that for the cationic flocculant, it has a great behavior. It has showed a great behavior. And regarding the values forecasted by the model and the experimental ones, they are really close together. For the anionic flocculant, the so we verify that the highest influence came from the flocculant dose and also from the pH. And as you can see in the table, the average difference. And you can also see the values forecasted by the model and the experimental values. They are close to one another, but not so close as the cationic flocculant. Regarding the non-ionic flocculant, the results were the following: that the greatest influence was caused by the pH, and after that, the coagulant dose. And this can be seen in the table in the average difference. Via this chart, I analyze the experimental data compared to the model, and you can see they are not very close when it comes to the cationic flocculant. What have I concluded based on that? That the mineral sample has about 80% of calcite, lower amounts of dolomite, apatite, and biotite. That the optimization of the results using the ascending step methodology indicated that the cationic flocculant as well as the anionic flocculant were the best. And so 63.54 grams per ton was the dose of the coagulant, and 22.04 grams per ton was the dose of the flocculant. And with this optimization, the highest speed of sedimentation was 1.09 times 10 minus 1 centimeters per second. Analyzing the flocculants that had the best performance, we had a dose of cationic flocculant that was 20 grams per ton, and the sedimentation speed was 0.6 centimeters per second. And the highest speed was 1.09 times 10 minus 1 centimeters per second. And so analyzing the flocculants that had the best performance, the dispersed pulp had a natural pH, and the flocculant obtained the highest sedimentation speed. And I concluded that via these experiments and also statistical methodologies, the use of aluminum sulfate coagulants, okay, for the sample analyzed, reduces the sedimentation speed. So whenever we work with pre-coagulants, the pulp diminishes its sedimentation speed. So that's it. Thank you very much to all of you for your attention. And thank you very much.
Thank you for the presentation, Patrícia. Good morning, everyone. My name is Anna. I'm a mechanical engineer, expert in processes. I would like to ask you whether the solids used in the tests were generated particles or natural fines. Natural fines from Vale. And what is the size that you used? I don't remember exactly. I will tell you later. Okay, thank you. Thank you very much, Patrícia.